Hello everybody, welcome to the talk. I'm Brian Sharpe, Senior Rendering Developer at SideFX. Today I'll be discussing Karma XPU, SideFX's new OpenUSD-based GPU-CPU renderer. So what does this talk about? First, there is an introduction to Houdini, Solaris, OpenUSD, and MaterialX. Then I'll discuss Karma XPU and our upcoming version 1 release. I'll then give a quick overview of some of the latest features. And to finish, I'll give some technical details on how Karma XPU and some of the new features are implemented. So given the audience in this room, I probably don't need this slide, but I'll go through quickly anyway. So first off, what is Houdini? Houdini is a visual effects creation package used for film, TV, and video games. Its fully procedural workflow allows for easy creation of visually rich assets and visual effects. Houdini has existed for over 25 years and is a staple for anyone working in the visual effects industry. What is OpenUSD and what is Solaris? OpenUSD, with the USD standing for Universal Scene Description, is an open source 3D scene description and file format used for content creation and interchange between tools. It was initially developed by Pixar, but has fast become an industry standard within the visual effects industry. Solaris is a suite of look dev, layout, and lighting tools within Houdini, which are used to create and edit USD scenes. Solaris also makes use of Hydra, USD's rendering framework, which provides a plugin system for renderers. This means Solaris is compatible with many different renderers, such as SideFX's Karma, which I'll talk about soon, Pixar's RenderMan, Autodesk's Arnold, Maxon's Redshift, AMD's ProRender, and more. Before I get into Karma, I'll quickly mention MaterialX. At SideFX, we embrace open standards, as it really empowers our users by giving them flexibility. To that end, we've adopted MaterialX. MaterialX is an open standard for representing materials in computer graphics. It's open source, part of the Academy Software Foundation, and already has widespread support in the industry. Houdini allows for creation of MaterialX directly within its VOP Node Graph UI. It's even possible to mix MaterialX nodes with other Houdini native nodes. So it really has fit naturally into Houdini. So what is Karma? Karma is a Hydra-based renderer developed by SideFX and designed for use with Solaris. But being Hydra-based, it also works with other USD Hydra-based applications. What you can see in this image is Karma working in the standalone USD View application. Karma CPU is the CPU-only version of the renderer and is currently fully featured and production-ready and is now out in Houdini 19.5. It supports both FX and MaterialX for shading. What is Karma XPU? Karma XPU is a GPU-capable accelerator for Karma. It's not designed to replace Karma CPU, but rather be a high-performance alternative with a reduced feature set. XPU means that rendering can happen on both GPU or CPU, producing identical results on each, or both at the same time. And it's multi-GPU capable, meaning adding GPUs improves performance in a linear manner. Karma XPU is very fast. We're often seeing a 10 to 20x speed up with a single GPU. It supports MaterialX for shading, and it's currently available in beta in Houdini 19.5, and we'll be releasing version 1 Gold in Houdini 20 later this year. So what are the benefits of XPU? Firstly, it makes use of all resources on the computer. It's multi-GPU. It's also fail-safe, meaning that if a device fails, for example, runs out of memory, the other devices automatically pick up the load and finish the frame. Another advantage is that any scene will run on any machine. So if a scene is authored on a high-spec machine, it can still be run on a lower-spec machine, even one without a GPU. Rendering can be scheduled on a CPU render farm or GPU render farm. The results will always be the same. This gives flexibility to wranglers in large studios. Now, before I talk more about XPU, I'm going to show this cool video that we've got from the community. Let's see if it plays. Enjoy. XPU footage. Okay, so now onto some new features that are coming in Houdini 20. We've really worked on our volumes. They're now a first-class object with full support. So that means full AOVs, prim bars, light linking, light path expressions, the works. We've also optimized them a lot. We've added uniform volumes, which are used for oceans and fog. We've added frustum volumes, which is a common request from our more production-focused clients. We've also added more features to our base shader, so you can now mix two anisotropic lobes, allowing for sun halos and rim lighting on clouds. We've also added extinction and contribution modifiers, which allow someone to achieve a white puffy cloud with only a small number of bounces. We've improved lighting, so we've added geometry lights and also a physical skylight, which is like a procedural dome light which simulates a physically correct sky. With it, you can achieve sunsets on the horizon and such. We've added IES profiles and also light filter shaders, which are shaders which can be attached to light sources, as can be seen with this projector image. We've also improved sampling across the board, meaning lighting overall is more efficient. We've improved our liquids. So that includes nested dielectrics, which is when you can have things like ice within water within a glass. There's also absorption, where transparency can change over depth. And also dispersion, which is when light splits into a rainbow when it refracts through glass. Here's this whiskey glass. It shows the nested dielectrics, and the ice cubes have subsurface scattering on them as well. Very cool. We've added a bunch of shading features. So that includes hex tiling, which is a nice way to tile a texture over a surface without it appearing repetitive. We have a room mapping tool, which creates a parallax correcting room effect, useful for buildings and cityscapes. We also support rounded edges as well as point clouds. We also have a new fur material, which extends the existing hair material to handle physically correct fur. So that includes things like the medalla, which is like a small cylindrical structure within the hair strand itself. People are doing cool things with the fur material, such as this eagle. The fur BSDF is used for the barbs on the feathers. Huh. Let's play that again. Cool. We also have a physical lens, which allows for special lens warps, blurs, and bokeh effects. We've added crypto matte and deep output, full color space support, and much more. We invite you to take a look when Houdini 20 is released later this year. So now onto some more of the technical details. First up, what is an XPU device? Any compatible piece of hardware is viewed as a device, meaning any number of devices found on the computer are used for rendering, meaning Karma XPU is also multi-GPU. Currently, NVIDIA GPU devices and CPU devices are supported. Other hardware will come with time. And this is an interesting diagram. You can see how Karma CPU is a completely different renderer from Karma XPU, even though Karma XPU has a CPU component to it. Here's a diagram showing the overall architecture of Karma XPU. Scene data comes in from USD through Hydra, shown on the left. Karma XPU then converts the scene data to a form suitable for the device rendering code to consume. The CPU device is able to start rendering immediately by reading the data directly from host memory. The GPU device must first copy the data from host memory to its own device memory before rendering. The render is processed iteratively, meaning a fixed number of passes, by taking a fixed number of passes over the image, for example 128, firing a single path out of each pixel for each pass, and accumulating the result into the final image. XPU devices each render a single pass individually, with the index being determined by an incremental counter. They then accumulate it into the final image and are assigned a new pass to render. This process is repeated until the image is complete. It allows some devices to be more efficient than others, meaning some devices could render many passes and others only a few. Random number generators are indexed by their pass ID, meaning this process is deterministic. So rendering on one system will produce the same result as rendering on another with a potentially different setup. If a device fails mid-render, then its incomplete pass will be picked up and rendered by another device, meaning the system is very fail-safe. If those two slides seem familiar, it's because we gave a talk at GDC 2022 on the architecture of XPU, which went into much more detail than you've seen today. For anyone interested, I suggest you take a look. Now onto some newer features. We've added subsurface scattering, which allows for effects such as skin and snow. We've implemented standard random walk subsurface scattering. The steps taken are for the path to first enter the mesh using a Lambertian profile, seen as this red semicircle. We then randomly walk within the medium. If we hit the mesh again, we move the path to the exit point and continue, again via a Lambertian profile, seen as this blue semicircle. Otherwise, we terminate the path, so we have an upper limit on the number of steps we can take. The mesh should be manifold. Multiple importance sampling can be used to handle chromatic extinction, such as in this Disney paper. We thought divergence might hurt performance, but it's been fast in practice, so we're very happy with the result. Up next is uniform volumes. So uniform volumes are homogeneous volumes bounded by a manifold container mesh and are often used for oceans and water. As shown in our previous architecture talk, our volumes are handled by ray matching in an intersection program. But how can we ray match the interior of a mesh without firing rays during the ray matching step, because optics doesn't allow for that? What we do is first launch a single spans ray through all the container meshes. It uses an any-hit program to capture a sorted list of the closest n hits. A hit point is stored as its distance, whether it's a front face or back face, and its object ID. And because we don't need to execute the shader to collect any of that information, it's fast. The list is then used by the path tracing ray to correctly ray match the interior of the container mesh. Now for some lighting gems. We have improved sampling on our cylinder lights, which now take into account both distance and angle along the central axis of the cylinder. So you can see this in this white diagram. Even though the cylinder is the grey box, we sample along the central black line there. The assumption being that cylinder lights are usually long and thin. And if we get a short one, then sampling reduces to uniform sampling anyway. Anyone wanting to experiment with this themselves should look into techniques such as equiangular sampling, as in this paper by the Arnold guys, and also product sampling, as in this paper by David Hart and others at NVIDIA. We also now clip light geometry where possible. So that will be conservatively clipping against the plane defined by the surface position and shading normal. We do this for both cylinder and rectangle lights. And because the light still retains its original shape, so a rectangle stays a rectangle and a cylinder stays a cylinder, we can continue to use existing techniques to sample the clip shape. So here are some images showing the combining of the techniques. Apologies for the contrived scene, but it's okay. This is a rectangle light using standard spherical triangle sampling. Then we add in product sampling, then eventually clipping, so that you can see the box on the left there changed. And again, spherical triangle sampling, product sampling, and clipping. Now with cylinder lights, here's standard uniform sampling, here's equiangular sampling, and here's equiangular sampling with clipping. So again, the box on the left has improved with the clipping. So going back, uniform sampling, equiangular sampling, clipping. Now I'm going to acknowledge some NVIDIA tech that we found useful while developing XPU. Optics 7 has been very good. We fully recommend. In particular, the curves are very fast. Our customers are often commenting on how fast their hair and fur assets render with XPU. There is NVRTC, which is NVIDIA's runtime C++ CUDA compiler, which has been great for our runtime shader compilation. A tip for anyone wanting to deploy software that uses NVRTC is to look into the Jittify project, which provides placeholders for the C standard library. We've made use of the new self-intersection avoidance library, which has been used to implement our automatic ray bias feature. NDL has also been very useful. It implements MaterialX, and it's open source, which allows for flexible use, as well as being a great reference for BSDF math. And then there's NanoVDB, which has given us very fast volumes. And before I finish, I'd like to acknowledge the other hard-working members of the SideFX rendering team, as well as the many others from SideFX, and also the Houdini community for helping out with that awesome clip. And with that, thank you. And we're open for questions.
We are open for questions.
Hi, Brian. I have questions.
Yeah.
You mentioned something really interesting in an earlier slide, the volume modifiers. Could you talk a little bit more about that?
Volume modifiers.
Yeah.
Yeah, so what happens when you scatter through a volume is that both opacity and scattering are linked. So when light normally hits a surface, you define like a diffuse color, and it shines that amount of light back to you. With a volume, it's slightly different. You could set it to be gray or white or whatever, and it shines that amount of light to you, but it's also removing that amount of light from the ray that's passing through. So often artists find this contradictory sort of feel where they want to make a cloud brighter by dialing up the reflectance, but it actually gets darker because the absorption's increasing as the rays firing through the cloud. So what we've done is we've just broken the rendering equation a little bit there, or the math. So what you can actually do is you can boost up the reflectance of the cloud without increasing the extinction. So it's a little non-physical hack. What we expect people to do is punch in, 300 bounces, get a white cloud, and then dial in 8 bounces with these modifiers to get the same looking cloud, and then do their animation.
Okay, cool. You mentioned sky models as well. What are you using for your physical sky?
That's the one from Alex Wilkie.
Oh, yeah.
Yeah, so it's a 2012 one or 2013 one we're using. There's one that came out in, I think, about 2019 or 2020, but it has a lot of data that goes with it, like gigs, and we didn't want to include increase people's downloads.
Cool. Sorry, last one. You mentioned the renders from CPU and GPU are the same.
Yeah.
Like how the same? Like are they like?
Oh, they're very close. So the only difference we have is just numerical precision, and we've kind of stamped those out like whack-a-mole anyway. So all the features like curves, points, geometry, volumes. Well, the way we wrote our Embry renderer is we basically made it behave like optics. So Embry allows for intersection shaders or programs, but it's called something else. It's called a filter function or intersection function or something. The AnyHit program is called a filter function, and then there's a closest hit you can kind of. So I emulated those inside of Embry, and then we just made sure as we were writing both devices, we made sure that they behaved exactly the same. With the geometry, we've chosen, for lack of a better word, a lowest common denominator approach. So with curves, optics curves have to have backface culling on them. You can't have the curves any other way. So we force backface culling on the Embry side as well. And with points, that behave slightly different in optics versus Embry. So I use the Embry points natively, but in optics, I wrote my own. And yeah, but we've ironed out all the little differences in it, and it works pretty well.
That's very impressive. Thank you.
Will it be possible in the future to have like a geometry procedural that work in Karma XPU, like generating geometry on the fly at render time?
Render time. In the current architecture, no, because we don't have any runtime compiling happening on the CPU, and we talk about that in our previous talk as well. So optics, the GPU has runtime compiling with NVRTC, but in the CPU we don't. We compile everything up front. But we hope to address that in the coming releases. So once we get runtime compiling working on the CPU as well, then I think we could start addressing what you've asked. But at the moment, no, sorry.
Thank you.
Talking about the equiangular sampling, those sorts of improvements, is that going to also make its way back into Karma CPU?
It's already in there.
Ah, lovely. Great. That's it.
Perfect.
Easy answer.
Yeah.
Other questions? Yeah, over here. I'll go here and then over to you.
So with Karma XPU being able to render just like on the CPU only, as well as like on CPU plus GPU, I'm curious if there's any chance that like at some point it could get like to be even faster than Karma CPU on its own, just given that it has like a more limited feature set. And then also I'm curious, like for me, I've been liking sort of hopping between CPU and XPU and doing my final, animation renders with XPU, and then just benefiting from like the really fast sort of like time to first pixel previewing with like, a CPU with lots of cores. And I think a lot of people who have used XPU have noticed that like it'll give you like a really quick time to first pixel, and then it will kind of pause for a second while it's loading on optics. Is that, because that would be sort of the dream, is if it could just start rendering on CPU and then keep doing that while it sort of loads on the GPU. Is that something that is like being looked into or could be addressed, or is that like a limitation of optics or something?
I think there are two questions there in your question. I'll answer the second one first. So what that stall you're encountering is the runtime compiling of NVIDIA RTC. So we've improved that a lot for XPU. So instead of it's probably 4 times faster, but there's still a noticeable pause there. We are working with NVIDIA with feature requests and whatever to make that even better. So XPU, we're improving it, and we acknowledge that pause is an issue for people, but it's improving. Going back to your first question with Karma CPU, will Karma XPU's CPU version ever run faster than the original CPU renderer? It's hard to say, because it's not apples for apples, and there's some things that XPU does faster than CPU and the other way around. One thing that the Karma CPU has is it has a lot more flexibility in what it can write. XPU has to balance the algorithms with what's going to run on the GPU as well as what we can do on the CPU, and we kind of have to make them match. On Karma CPU, just because it has only the CPU available to it, it can do a lot more. So it's actually got a lot of features that we don't have yet on XPU, such as it's got path guiding. And it also has something called a variance anti-aliasing. It's a technical name, but it basically means that it learns over time where the specular noise is, and it tries to resolve it as it's rendering. So it's always easier for Karma CPU to code up those features, and we don't have them in XPU yet. So yes, XPU is more streamlined, but Karma CPU has more magic, and has additional magic that we don't have on this side. So I don't know. I can't answer that first question. Sorry.
Gotcha. That makes sense. Thank you.
Getting my steps in.
Regarding the ocean spectrum displacement, is there a specific workflow for XPU?
No, we try and keep the workflows the same. So XPU should really just behave like CPU. It's just that XPU sometimes doesn't have the features that Karma CPU does. There are some ocean tools that are available now, and they should work for both Karma CPU and XPU. I don't exactly know how to use them, what their names are. Sorry, I don't sit on the artist side of it. But rest assured, when Houdini 20 comes out, you'll find some tools that can build oceans for both renderers, and they'll behave the same in both.
Okay, thanks.
Any others?
Just curious about the latest with if you, out of core rendering on the GPU, if you use more memory than you're seeing as more memory use than memory available on the GPU. How does it handle that?
Yeah, that's it. We're constantly improving it. It's not something you can have just all going all at once. So it's something we're just chipping away at. At the moment in 19.5, we have something called demand loading. So it's demand loading of sparse tiles on the textures, and as well as primvars. So you could have a particle sim that could have 1 million primvars or 1,000 primvars, and the GPU will only load the ones that are necessary. what we're working on for 20 is that we're going to be evicting data back out of the GPU as well. So we will go out of core. The question is, what performance will you get when we're doing that? And that's still very scene dependent, and we're still working with the code at the moment. So we can't give you metrics. So there will be some out of core, but I wouldn't expect that XPU is going to run at the same speed while it's doing out of core stuff. The performance will drop significantly because you're going to be spending more time doing swap than we are actually rendering, but it should be better than the GPU just completely shutting off like it does now and just leaving only the CPU. So you'll have a CPU and a slow running GPU instead of just the CPU that we have right now. Did that answer your question?
Yeah, I think it does. And then a quick follow-up would be, is it kind of targeted a little bit more towards batch out of core with the paging stuff that you're mentioning, or interactive out of core in terms of the performance metrics that you're targeting first and foremost? Some out of core schemes would maybe perform better in interactive versus batch. Are you targeting one or the other and prioritizing that?
At this moment, we're not, but that doesn't mean that we won't when we get closer to release.
Thank you.
Any others?
You mentioned like future support for other non-NVIDIA hardware. Can you discuss that at all?
That will come with time, but we haven't addressed it in this release.
All right.
What I'm saying is that we're not close to the idea, but we haven't put development time into it for Houdini 20 yet.
Okay. And another quick question coming on the heels of the previous lecture about AI. Are you guys thinking about implementing some AI-related technology into Karma XPU, such as, for instance, upresing a render, using some of the upresing technology so that you can kind of maybe render at a lower resolution and then kind of get like a higher resolution result that looks pretty good?
Yeah, we'd love to do that stuff more. At the within the renderer, at the moment we're relying on the post-process denoisers that exist already. So that's the Intel denoiser and also the NVIDIA one, and both those allow for some upresing, but it's always limited when you can just give a denoiser just an image and only an image, and it just goes from there. We'd love to get to the world that we give it the image and some more information, and then possibly even some feedback, but we're not at that stage yet. Houdini 20 will just be giving the image to those denoisers, and they will just do their work.
Gotcha. Thank you.
Any others? Yeah.
In your experience, did the two denoisers have any particular strengths? Are there situations where you'd use optics? Are there situations where you'd use the Intel denoiser?
Yeah, the NVIDIA one is much faster. So the NVIDIA one can run almost interactive speeds, but the Intel one gives a better result overall. But they're both changing rapidly. So what the answer that I've given now will probably be different in 3 months' time. What's been announced is the Intel guys have put their one now on the GPU. So traditionally the Intel one ran on the CPU. So now that the Intel one's running on the GPU, it might get to the same speed as the NVIDIA one, but I haven't had a chance to try that out yet, so I don't know the exact speed.
Thank you.
Any others? Going once, going twice. All right, well, thanks very much, Brian. Excellent.